Now we will discuss some problems based on the function. Okay. Um, this exercise, first you want to show that suppose f is 1 to 1. Okay, f is 1 to 1 mapping if and only if f of a intersection b equal f of a intersection f of b. Okay, f of a intersection b if and only if f of a intersection f of b. Okay. 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 Uh, you want to prove that f is 1 to 1 if and only if f of a intersection b equal f of a intersection f of b. Suppose that f is 1 to 1. Let a comma b two sets, these are the subset of x. Let you take one of the element y belong to f of a intersection f of b. Okay. This one implies now you take f is 1 to 1, you want to show that this condition. These are y belong to f of a and y belong to f of b. Y belong to f of a means y equal to for f of x1 belong to a1. For some s1 belong to a, and y equal f of x2 for some s2 belong to b. Okay, for some s2 belong to b. Okay, for some s2 belong to b. Now, right now you have y equal f of x1 f of x2. Okay, s1 belong to a and s2 belong to b. But f is 1 to 1, therefore x1 equal to x2. F is 1 to 1, therefore x1 equal to x2. Therefore y equal f of x1 for some here s1 s2 are equal, therefore you can put x1 belong to a intersection b. This one implies y belong to f of x1 belong to a intersection b, no, therefore y belong to f of a intersection b, right? Suppose y belong to f of a intersection f of b, we prove y belong to f of a intersection b, therefore f of a intersection f of b subset of f of a intersection b. It is your first condition. Okay, it is your first condition. Now obviously this a intersection b subset of a and a intersection b subset of b. Therefore, f of A intersection B subset of A and f of A intersection B subset of FB. From this both you will get f of A intersection B subset of f of A intersection f of B. It is your second condition. 1 and 2 implies f of A intersection B equal f of A intersection f of B. Right? For a converse part, conversely suppose that f of A intersection B, f of A intersection f of B. We use this one, you want to prove that f is 1 to 1. Okay, f is 1 to 1. Okay. Now, okay, assume that A equal to x1, B equal to x2. Here x1 not equal to x2 and x1, x2 belong to x. Therefore, obviously A comma B subset of x. And what is the A intersection B? A intersection B should be empty. Suppose A intersection B empty means f of A intersection B, right? F of A intersection B equal again f of empty. There is no element for A intersection B. F of empty again empty set. You want to show that f is 1 to 1, you know, right? You take first s1 not equal to s2, then you want to show that f of x1 not equal to f of x2. That is also another way to show that it is 1 to 1, right? Now your claim is you want to show that f of x1 not equal to f of x2. Now you have this condition f of A intersection B right. Now you have this condition f of A intersection B equal f of A intersection f of B. Here f of A intersection B empty. Therefore, this empty equal f of A intersection f of B. Right? Okay. you know here you have, right, here already we assume that x1 not equal to s2. Okay, it's not equal to x2. Here f of a and b empty. Okay, f of a and b empty. This one empty means this one empty, this one empty. But you know here, but you have f of a equal to x1 set, no? This set, right? For f of a, okay, f of a. At least one of the fa or fp empty is enough to show that this is np. Therefore, right, f of x1 empty or this f of b is equal to f of s2 is empty. Okay. But here f of x1, right, here you have for a is set you have only one element x1. Therefore b is one of the set, only one element x2. Therefore this one, suppose these two sets are equal, right? Suppose two sets are equal, understand, suppose two sets are equal, here x1 element, here also x2 s1 element. Therefore the x1 element is common for here. Suppose x1 two elements are equal, I mean x1 equal x2 means you put here x1 and x1, therefore common element x1, therefore f of x1 non-empty, right? If you take f1 x1 equal x2, we can't arrive this condition. We can't arrive empty equal f of a intersection f of b. Therefore, if x1 equal x2, then f of a intersection b non-empty. But we have f of a intersection b empty for this case. Suppose f of a intersection b empty means your x1 not equal to x2. Therefore, x1 not equal to s2 means your f of x1 value is not equal to f of s2, because f of x1 value is not equal to f of x2, because suppose if f of x1 equal f of x2 means you can put f of x1 intersection f of x1. For this 2 you will get f of x1, both are same. Then it's not an empty set. We already know that, no, f of x1 not equal to s2, f of x1 not equal to empty, this one not equal to empty. Therefore, here only possible for f of x1 not equal to f of x2. Okay. We take this x1 not equal to s2, we prove f of x1 not equal to x2. Therefore, f is 1 to 1. It is another way to solve that. You want to show that it's another way to show that f is 1 to 1. Therefore, it is the converse part of this exercise. Okay, it is the converse part of this exercise. Next exercise. Next exercise. You want to show that exercise number 2. You want to show that f is 1 to 1 if and only if you want to show that f of a intersection b equal f of a intersection, sorry, f is 1 to 1, f of a minus b, f of a minus b equal f of a minus f of b. Okay, this part now we want to do. F is 1 to 1, if and only if f of a minus b equal f of a minus f of b. Suppose that f is 1 to 1, right? Suppose that f is 1 to 1, right? Suppose that f is 1 to 1. You take let, you want to show that this condition. Uh, you take let y belong to f of a minus b. You know, obviously this one true. Just wait. Obviously this, if we can only we prove f of a minus f of b, f of a minus f of b subset of f of a minus b. For this one there is no condition to show this one, right? Suppose if f is 1 to 1, you want to show the remaining part, that means f of a minus b subset of this one, f of a minus f of b. For that, then only we can say that it is equal, right? Now you take let, you want to take one of the element for this set, y belong to f of a minus b. Therefore y equal f of x for some x belong to a minus b. Now you take two element for x. That means here y equal f of x1 for some, here your x1 belong to a minus b, right? S1 belong to a minus b. Okay, S1 belong to a minus b. That means but you want to use the one-to-one condition here also. Okay, one-to-one condition here also. Now y equal f of x1 for some x1 belong to a and x1 does not belong to b. Now you take another element, right? If you take another element, right, that means here you put here if y equal f of x2 for some, it is also possible, for some S2 does not belong to A and S2 belong to B. For this case also y equal f of x2, but y equal y both are same, right? It is possible, no? Right. Um, but suppose here x1 belong to A minus 1 means, suppose you put here x1 belong to A and x1 belong to B means it's not possible because A minus B. Therefore, suppose x1 belong to A, s2 belong to B. Therefore, s1 not equal to s2. Okay, s1 not equal to s2. Okay. Therefore, x1 not equal to x2. Okay, s1 not equal to s2. Now you want to show that which one, from the s1 not equal to x2 means, right, s1 not equal to s2 means f of x1 not equal to f of x2 because f is 1 to 1. F is 1 to 1. We want to use the condition 1 to 1. F is 1 to 1. Okay. F is 1 to 1. Okay, F is 1 to 1. Now f of x1 not equal to f of x2. No. Suppose f of x1 not equal to f of x2 means, right, f of x1 not equal to f of x2 means, right, here x1 belong to A and x2 belong to B. Therefore, you can write y equal f of x1 for some x1 belong to A, and y equal f of x2 for some x2 belong to B, right? Right. Therefore, this y equal f of x1, right, for some, here, here you can write f of x1, no, therefore x1 belong to A and s1 does not belong to B. Similarly, y equal f of x2 for some, right, for some x2 belong to, sorry, x2 does not belong to A and x2 belong to B. No. Now your claim is you want to show that y belong to f of A in this A minus B you take. You want to show that y belong to f of A minus y belong to f of B. That means first means if x1 belong to A, therefore x1 does not belong to B means, right, you take as a f of x1 first, right. This means belong to f of s1 belong to A and s1 does not belong to B means you will write f of x1 belong to f of a, and f of x1 means f of x1, okay, f of x1 does not belong to b. You know, x1 belong to a, okay, that means your f of x1 belong to f of a minus f of b, but f of x1 means your y belong to f of a minus f of b, right? Therefore you take, it is your y. Similarly, y equal x2, you can show that y equal f of x2, this one belong to f of which one, f of uh, y equal f of x2. From this one, f of s2 does not belong to a, f of s2 belong to b. Therefore f of s2 belong to b, then you can get like this condition, f of x2 f of a minus f of b, then y belong to f of a minus b. We take y belong to f of a minus b. Now we prove y belong to f of a minus f of b. Therefore you can write f of a minus b subset of f of a minus f of b. We use the addition condition on to condition, one to one condition, then prove that is both are here subset property exists, f of a minus b subset of f of a minus f of b. We already, obviously we already proved f of a minus f of b equals subset of f of a minus b. From both you will get f of a minus b equal f of a minus f of b. It is your second one, it is your first one. From this both you will get, right, it is your first one, right, it is your first one, right, it is your second one. From this both you will get is equal sign. Now remaining you want to show that converse part. Converse part. Conversely, suppose that f of a minus b equal f of a minus f of b. You want to show that f is 1 to 1. Your claim is f is 1 to 1. Your claim is f is 1 to 1. Okay. Assume that for sets a equal to x1, b equal to x2, both are not equal, and x1, s2 belong to s. Therefore, a comma b subset of x. What about a intersection b? There is no common element, therefore it's empty. But sorry, here you want to check a, not a intersection b, a minus b. A minus b. There is no common element for x1 s2, therefore it is also empty. F of a minus b, that is also empty. F of empty. Here a is one of x1 only one element x1, b only one element x2 elements. There is no common element. Suppose here a intersection b complement, all set x. Otherwise here not empty, no, because a minus b, no, here whole set X, union set S. Therefore, A intersection B complement, this is equal to A minus B. Here your set element X1 intersection B complement, right? B equal S2 complement. That means whole set, no? Because suppose here only S2 elements there, then to take S2 complement, not S2 other elements. Therefore, X1 also included and other elements also included. Therefore, it is your X1. Is it okay? It is your X1. You know, S2 complement means S2 also included, right? Sorry, S2 excluded, that other elements are there, but S1 there. Therefore, is intersection X1. Now, you want to show that F is 1 to 1, right? 1 to 1. Therefore, H1 not equal to H2. We assume that we want to show that f of x1 not equal to f of x2. F of x1 not equal to f of x2. We have this condition. Now you claim now you want to show that f of x1 not equal to f of x2. Right? Suppose here S2 belong to B, no? You have B equal S2. Therefore, what is the f of B? F of B equal f of x2. Right? And you have A equal to x1. Therefore, f of A equal f of x1. Right? But, right? Now you want to show that both are not equal, because what about f of A? F of A, you know that, right? F of A, you know that f of x1, f of x1, you know that here you take both sides f function f a minus b equal f of x1, f of a minus b. For this case, if you take fb, f of x2, right? F of x2 means f of x2 means f of x2, right? Here x2 belong to b, not a, right? Right? B, whether here is f of a minus b? No. This f of a minus b means, right, f of a minus b means a minus b consists element only x1 only, right? This one not equal a minus b, because f of x2 here, f of x2, f of b equal f of x2, right? F of b equal f of x2, but this f of x2 does not belong to this in this set, no, does not belong to in this set element. Therefore, right, suppose this one equal, both are equal means this one equal. Here equal, okay, because f of x1 equal, obviously true, f of x a minus b equal f of x1, okay. For f of b equal f of x2, but this f of x2 not included this f of a minus b, therefore it's not equal, therefore equal here not equal, therefore both are not equal, right? F of a, f of b, f of x1 not equal f of x2. It is enough to show that. Suppose we take x1 not equal to x2, we prove f of x1 not equal to f of x2, therefore f is 1 to 1. Therefore f is 1 to 1. Okay, therefore f is 1 to 1. Next question. You have to prove that next question. Right, you have to prove that. Suppose a comma b subset of y and f h to y is a function, then so that there are 6 properties, right? You want to show that these 6 properties. Okay. exercise, let a comma b subset of x. So the function f x to y is a function, let be a function. You want to prove that first condition, first part, if a subset of b, then let f inverse a subset of f inverse a. Second part, if then what we want to prove that f inverse a union b equal f inverse a union f inverse. Third part, we want to show that f inverse a intersection b equal f inverse a intersection f inverse. Fourth part, f inverse a minus b equal f inverse a minus f inverse for c all for c subset of x. So we can gives you a comma b comma c subset of x. Therefore, we can show that this c subset of x inverse f of c. So for the f of f inverse b, the b also subset of x subset of all c subset of x all c. Okay, here you want to prove these parts, right? You want to prove these parts. First part, a subset of b, then right a subset of b, then uh, f of a, f inverse of a subset of f inverse of b. Second part, f inverse of a union b equal f inverse a union f inverse b. Third part, f inverse a intersection b equal f inverse a intersection f inverse b. Fourth part, f inverse a minus b equal f inverse a minus f inverse b. Fifth part, c subset of f inverse fc. And sixth part, d sub f of f inverse d subset of d. For the first part, now we will do, right? You take one of the element from this set first. Let x belong to f inverse a. What is the next step? then you can write f of x belong to a for some x belong to a. We have a subset of b, therefore this f of x belong to a subset of b for some, now your a x belong to b because a subset of b, no? This one implies f of x belong to b. This one implies x belong to f inverse of b. Now we assume that x belong to f inverse of a, we prove x belong to f inverse of b, therefore f inverse of a subset of f inverse of b. This is your first part. Second part, f inverse a union b equal f inverse a union f inverse b. Let x belong to f inverse a union b. This one implies f of x belong to a union b. This one means f of x belong to a or f of x belong to b. This one implies, right? From this one implies x belong to f inverse of a or x belong to f inverse of b. S belong to f inverse of b. From this one implies x belong to f inverse of a union f inverse of b. Reverse part also true. That is f inverse a union b subset of f inverse a union f inverse b for this part. The reverse part and f inverse a union f inverse b subset of f inverse a union b. From this both you will get, therefore f inverse a union b equal f inverse a union f inverse of b. Okay, f inverse union f inverse of b. Okay, third part also equal sign. Let x belong to f inverse a intersection b. You will take a intersection b. This one implies, right, f of x belong to a intersection b. This one implies f of x belong to a and f of x belong to b. This one implies x belong to f inverse a and x belong to f inverse b. This one implies x belong to f inverse a intersection f inverse b. And reverse part also true. That is, first this one, f inverse a intersection b subset of f inverse a intersection f inverse of b and f inverse of a intersection f inverse of b subset of f inverse of a intersection b. From this both you will write therefore f inverse of a intersection b f inverse of a intersection f inverse of b. Okay, it is your third part. Now move to the fourth part. Okay, okay, now let your fourth part let you take one of the element from this set. Let x belong to f inverse a minus b. Then you have f of x belong to a minus b. F of x belong to a minus b means f of x belong to a and f of x does not belong to b. A minus b, no. Therefore, this one x belong to f inverse of a and s does not belong to f inverse of b. Therefore, s belong to f inverse of a minus f inverse of b. Okay, f belong to f inverse of a minus f inverse of b. Okay, that one means x belong to f inverse a minus b. We prove x belong to f inverse a minus f inverse b. Therefore, f inverse a minus b subset of f inverse a minus f inverse b. Okay, minus f inverse b. Here reverse inclusion also satisfying. Therefore, and similarly reverse inclusion also satisfying. F of f inverse a minus f inverse b subset of f inverse a minus b. Therefore, f inverse a minus b equal f inverse a minus f inverse b. Here this reverse inclusion. Therefore, this reverse inclusion also satisfying. Therefore, f inverse a minus b equal f inverse a minus f inverse b. Question number 5. Right. You take let x belong to C. Then this one implies f of x belong to f of C. Therefore, x belong to f inverse of f of C. This means C subset of f inverse of f of C. For all C belong to, for all C subset of x, for all C subset of x. Okay, for all C subset of x. Now part 6, let you take the d subset of y. Okay, sorry, here d subset of y, d subset of y, let one of the element y belong to f of f inverse d. You will take, therefore you can find such element for this part. Then you can write y equal to f of x for some, right, this x belong to this one, f inverse d, implies y equal f of x for some f of x belong to d. That means y equal f of x, here f of x belong to d. That is, y belong to this one, we prove y belong to d. Therefore, f of f inverse d subset of d. Okay, subset of d, right? Okay, next question. exercise, you want to show that f is 1 to 1 if and only if you want to show that a equal to one of the set a subset of x, a equal to f inverse of f of a for all a subset of x. You want to show that this part, right? F is 1 to 1 if and only if a equal to f inverse of f of a subset of x. Okay. Okay. Suppose that f is 1 to 1. For any function, we use the previous exercise. The previous exercise we prove something, right? For any function, this one true. A subset of f inverse of f of a. This one true first. Right? We already prove here for all a subset of x. Now your claim is you want to show that uh, f inverse f of a subset of a. Let you take one of the element x belong to this part f inverse of f of a. From this one, your f of x belong to f of a, right? Then you will write equal condition f of x equal for any element for some y belong to a. For some y belong to a. From this one implies f of x equal f of y, but f is 1 to 1, therefore x equal y because f is 1 to 1. X equal y, therefore x equal y means this one belong to a. That means x equal y, this one belong to a. We already assume that x belong to this one. We prove x belong to a. So it implies x belong to a. Therefore, f inverse of f of a subset of a. Second one. Therefore, 1 and 2 implies f inverse of f of a equal a. For all a subset of x. Now for a converse part, right? Conversely suppose that f inverse of f of a equal a. You want to show that f is 1 to 1. Right? We shall prove that f is 1 to 1. For that one, let you take f of x1 equal f of x2. x1, x2 belong to x. Take one of the set a equal x1, right? A equal x1. Then by assumption saying that f inverse of f of a equal a, no? Then a equal this set, you can write f inverse of f of x1 equal this x1. Okay, my assumption. Similarly, suppose if a equal x2, okay, if a equal x2, then by the assumption f inverse of f of x2 equal x2. Okay, Now we take f of x1 equal f of x2. These are both are equal. F of x1 equal f of x2. For this condition, you take inverse both sides. This means f inverse of f of x2 x1, f inverse f of x2. You take for this part, take both the inverse. We have this value is equal to x1, this value equal to x2. We have this part is equal to x1 equal x2. Only one element, both are equal means x1 equal x2. We assume that f of x1 equal f of x2. We prove that x1 equal x2. Therefore, f is 1 to 1. Therefore, f is 1 to 1. Only one element, right? x1 set. Therefore, that one x1 equal to that x2 element, only one element x2. Therefore, x1 equal to x2. Therefore, f is 1 to 1. Next question. Next question based on the if is on to condition, right? If is on true. Next question exercise if is on true, if is on true, if and only if you want to show that b equal f of f inverse b for all b is subset of y. This part you want to prove. For this for to prove this part also we use some previous parts, right? That means for any function we prove now. For any function, suppose that f is 1 to 1, f is on 2. Suppose that f is on 2, right? For any function we have, right, using the previous sum properties, you already proved f of f inverse of, you put d as a b, you can write f of f inverse b subset of b. Previous part you already proved f of f inverse d equal d. Now you put b as in terms b as a d as a b, then you will get this one. This first. Remaining you want to show that for the equal condition, remaining you want to show that b subset of f inverse b. Your claim is b subset of f inverse b. Okay. Let y belong to b. Then for f inverse of y belong to f inverse of b. Here f is onto function. Since f is onto function, therefore we have f of x equal to y for all x belong to a, y belong to b, right? F of x equal y for all x belong to a. This one means here f of x equal y, y already, y belong to b, b subset of y, no, y belong to b. Therefore, this one implies f of x belong to b. This one means x belong to f inverse of b. Now you take both side f, then f of x belong to f of f inverse of b. But f of x means y, because f is on true. Y belong to f of f inverse b. F of f inverse b. We take y belong to b, we prove y belong to f of f inverse b. Therefore, b subset of f of f inverse b. This is your second part. First, for any function this one true, now we have this part. Therefore, 1 and 2 implies b equal f of f inverse b. b equal f of f inverse b. Now, for a converse part, conversely suppose that b equal f of f inverse b. You want to show that f is onto. Claim f is onto. You take, right, take for a set b consists one of the element y1. Therefore, b subset of y. Then obviously b subset of y. Y1 belong to y. Using by assumption, you have your set is y1. You can write y1 or otherwise y. So y, okay, y, okay, y. This one f of f inverse y. You have y f of f inverse y means f inverse y. Okay, now we can use this condition here. Okay, here f inverse, here b, right? F inverse y. Therefore, here y belong to b, right? Y belong to b. Y belong to b. F is function from x to y. Then you can write here one of the element f of x1. Your element equal f of x1, right? F of x1 or x, okay, x, right? This one implies, right? Here one of the set y, here one of the set x. Therefore, this result is true for each element. That means y equal f of x, right? That is directly is x belong to x such that f of x equal y, right? For all this y belong to b. Y belong to b because b is subset of y. This condition satisfying, therefore f is onto. Therefore f is onto. Okay. F is untrue. Right? These are the based on the functions problems, right? Function problems, right? Here major things is first you want to understand how can you show that f is bijective function. You want to show that f is one to one and on to, then you can say that bijection. We have used some theorems part. Then you can show that f is suppose f is function is bijection. Then you can say that f is invertible. Then you can find the f inverse function. Then you can do some properties of the composition function, right? For a composition function, right? How can you find the composition function? And um, you do some you prove some properties based on the function, right? Okay. Now I will do some problems based on the relation. Okay, based on the relation. These are the functions. Now we will do some problems based on the relation. Now we will do this problem exercise. See, this is based on the relation, right? Based on the relation question. Relation question first. You can for a comma b comma c comma d belong to R squared, define, right, a comma b related to c comma d if and only if 2a minus b equal to c minus d, so that this is an equivalence relation on R squared. First, to take two elements. Suppose here a comma b, again a comma b belong to R squared, means here 2a minus b equal to 2a minus b equal c also again a, therefore 2a minus b again. This one, if and only if this condition satisfying, a comma b is related to again a comma b. This one means again same element a comma b. Therefore, this relation is reflexive. For a symmetric, let you take a comma b, c comma d belong to R squared. Then you want to show that c comma R squared. Now you have this one, a comma b is related to c comma d if and only if you have this condition 2a minus b equal 2c minus d. Now you can take the if and only if this one, you can take the b in first b, otherwise you take here this one first, 2c minus d equal 2a minus b. This one means first c comma d is related to a comma b. Okay, c comma d related to a comma b, which one called as a symmetric relation. Okay, therefore this is symmetric. This one is symmetric. C comma d related to a comma b symmetric. For transitive, let a comma b, c comma d, e comma f belong to R squared. Then you have a comma b related to c comma d and c comma d related to e comma f. On this 2 you have 2a minus b equal 2c minus d. On this point you have 2c minus d equal 2e minus f. But 2c minus 2 d equal 2c minus d are equal, and you have 2a minus e equal 2e minus f. This one implies a comma b is if and only if a comma b, right, related to e comma f. This means this relation is transitive. Therefore, this relation is equivalence relation. Okay, this relation is equivalent relation. Okay, this relation is equivalent relation. For this, now we do this question. Exercise this question based on the partially order set. Suppose that R is a partial order on a set A. Partial order on a set A. Prove that R inverse also partial order. Therefore, you want to check R inverse reflexive and symmetric transitive. Let, since R is a partial order, therefore R is reflexive. R is reflexive means A comma A belong to R for all A belong to set A. R is defined on A. Okay. Set A, no? Therefore defined on A. Therefore, here again A comma A belong to R inverse also for all A belong to B. Therefore, R inverse also reflexive. Is reflexive. Since R is antisymmetric, that means let if take A comma B belong to R and B comma C belong to R implies A comma B. Sorry, A equal B. B comma A. Okay, A equal B. We have A equal B. Now you want to show that A equal B for R inverse case also. That is from this part. That is suppose A comma B belong to R means you have B comma A belong to R inverse and B comma A belong to R means A comma B belong to R inverse. Okay. For this case, right, you can rewrite this B comma A belong to R inverse, B comma A belong to R inverse, we have A equal B. This case also we have A equal B. That means R inverse is antisymmetric. That means R inverse is antisymmetric. That means B equal A, no? B equal A. A equal B, B equal A, both the same. R is antisymmetric. Next, for transitive, let A comma B belong to R inverse and B comma C belong to R inverse. You want to show that A comma C also belong to R inverse. And this one, you will write B comma A belong to R and C comma B belong to R. You can write first this one. C comma B belong to R and B comma A belong to R. This one you have C comma B, B, therefore C comma A belong to R. C comma A belong to R means A comma C belong to R inverse. Therefore, we take A comma B belong to R inverse, B comma C belong to R inverse. We prove A comma C also belong to R inverse. Therefore, R inverse is transitive. Therefore, R inverse is a partially ordered set. R inverse is a partial order. Okay. R inverse is partial order. Okay. R inverse is partial order. These are the exercises based on the relation.